So we have finally arrived to talk about the binomial theorem, which is a great and faster way to expand binomials taken to any integer, and I'll say any integer power. If you kind of notice the pattern, we always start off with the first term of the binomial. See if I can highlight this for you all. So this x, we look at it, it is involved in all of the terms. And pretty much what we're doing is we're taking the power of the binomial, and you see it counts down by 1 each time, and depending on how far you go. The very last term will not involve the first term, simply because if you kind of look at it, it's technically x to the 0, and x to the 0 is equal to 1. So that's kind of why you have a coefficient of 1 for the last term. Now, similarly, you can look at the second term in the binomial, and you will notice that the y starts appearing at the second term. Mainly, again, because we have y to the 0 is equal to 1. It does not show up in the first term, but as you move on, it starts counting upwards the opposite way. So y to the first power, y to the second power, y cubed, and so on, all the way till the very end, until you get y to the n. And again, that's the value of the exponent on the binomial. Now, what's really interesting is after we've kind of have a little more experience, we can look at these n choose 1, n choose 2, n choose 3, and so on. And you could actually compute them using combination notation. But really, all of this is also found by using Pascal's triangle. So I'd like to start off just kind of showing you with x plus y to the 7th power. And yes, it is true, if we had a lot of patience, we could multiply it out with distribution and FOIL and such. But the binomial theorem takes things a little bit faster. So let's start off with expanding it out. If I do have x plus y to the 7th, I'll write this on top. I'm going to use a little more space, so we have to be careful here. We'll start off with x to the 7th plus, now it's going to be kind of a pattern. We have 7 choose 1, x to the 6th, and now we take the second term, y to the first power. You want to write the first power in? Go for it. That helps me too. We move on to the next term. We have 7 choose 2. Now again, we're counting down with the x's. This will be x to the 5th, and we're counting up with the y's. So y squared. Next term, 7 choose 3. Counting down with the x's, x to the 4th. Counting up with the y's, y cubed. Move on to the next term. 7 choose 4. Now if we do this, again, we're counting down with the x's, x to the 3rd, counting up with the y's, y to the 4th. Keep going. You'll kind of know when to stop in a second. We have 7 choose 5. This will be x to the, well, x squared. It's a little easier to say it that way. So counting down with the x's, counting up with the y's, we have y to the 5th. We have 7 choose, oops, we'll make that a fraction. 7 choose 6. X to the first power, y to the 6th power, counting up on the y's, down on the x's. And finally, the very last term, you don't have to write 7 choose 7, you can. There's a nice little pattern there. And actually, I'll write that at the beginning just so that you all see it as well. We already kind of realized that that is a 1. But notice we won't have any x's. So that's what I was speaking about with x to the 0. And this is finally where we have the y value at the value of the exponent, y to the 7th. And if I didn't, I don't think I mentioned it over here, but I will as well. At the very beginning, you technically do have 7 choose 0. Well, we already kind of know that's going to be a 1. And then we don't really have a y term, but technically it is there. It's y to the 0. So that might help with some consistency if you're trying to remember. Like, I don't really spend too much time trying to focus on memorizing the formula. It's more of just recognizing the pattern as you move from term to term. So again, just kind of keep in mind, if you'll know your value of your second term in terms of your exponent, just by the fact that the exponents should always add up to the power of your binomial. So if you look in all these cases, I didn't write x to the 1, but I will. If you add up those exponents on the x and the y, they always add up to 7, which is the power of your binomial. If you remember, if all you remember is counting down with the x's, then it automatically gives you a clue on what the y values will be in terms of their exponents, because you're just counting upwards. Or you just have to know that they add up to 7 and you'll be good. So that's kind of a nice way. I really take care of the terms, the powers of the terms first. And now it's an issue of figuring out, what are the values of these? 7 choose 0, 7 choose 1, 7 choose 3, 7 choose 4, 7 choose 5, 7 choose 6, and 7 choose 7. And personally, I really like Pascal's triangle as long as my power is not huge. It helps me evaluate this without needing a TI, but I will show you, I'll show you both ways as well. So let's figure out those values. I'm going to build a Pascal's triangle, and you probably have experience with this, but it's really, really cool to see. So let me see if I can. Yes, there we go. I might need a little space on this one, so bear with me. I'll write it over here. Okay, starting off, 1 at the top. Then we have another 1 and 1. And then we'll be always having 1s on the diagonals. And then to get the middle terms, it's always adding the 2 terms above. So 1 plus 1 gives us 2. And then we have a 1 at the end. So if you're kind of keeping this track of this, this is actually, in a way, x plus y squared. So now we keep going. 1 plus 2 is 3. 2 plus 1 is 3. We have a 1 on the edge. That would be like x plus y cubed. And you're probably saying, oh, okay, I have to build this out a little bit more till I get to the 7. So we're just going to be patient. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So that gives me x plus y to the 4th, or at least the coefficients. Keep going. 1, 5. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is also 10. 4 plus 1 is 5. We have a 1 at the end. That's x plus y to the 5th. And then keep going, because we need like x plus y to the 6th. So notice our triangle grows a bit, our pyramid grows. So I'll move everyone over just a little bit to allow for that. So let's look at the next row. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. And we have a 1. This now leaves us with x plus y to the 6th. And what do we need? Something like x plus y to the 7th. So I'll write this in red so it stands out. So we have the 1. Okay, 1 plus 6 is 7. 6 plus 15 gives us 21. 15 plus 20 gives us 35. We have another 20 plus 15, so we have another 35. 15 plus 6, we have 21. 6 plus 1 is 5, and we have a 1 at the end. So here we are. Relatively quick way to figure out those coefficients. I kind of like to show you how they relate. Starting off with 7 choose 0. That is going to leave us with a 1 as the coefficient. Then we still have x to the 7th, and I won't write y to the 0 because it's already 1. Now, 7, choose 1. We'll go back and we notice we're on 7 as far as the Pascal's triangle is concerned. That's leaving with x to the 6th, y. 7, choose 2. Let's look at that a little bit closely. Go back. We've already taken care of this one. This one, we should be on 21. I like to mark them off as I go if I don't have it right by my side. X to the 5th, y squared. Moving forward, we already took care of the 21, so we are on 35 now. 7, choose 3. So that's going to leave us with x to the 4th, y cubed. Moving on, we already had that first 35. We have another 35. You're kind of like, why are they the same? I encourage you, look at the formula and see what happens. It has to do with the reducing. So 35, now we have x cubed, y to the 4th, plus, we already took care of our 35. We're just moving forward. We have a 21. That's 7, choose 5. Now all you're doing is attaching the powers of x and the powers of y factors. We've got taken care of the 21. We are now on 7, choose 6, which is equal to 5. X times y to the 6th. And then finally, 7, choose 7 is a 1. And we don't write the x anymore. We just write the y to the 7th. And now, my friends, see if I can shrink it down in our viewing screen a little bit. I know it takes a little bit of horizontal work as far as the paper is concerned. You don't necessarily have to write the 1s in front of the x to the 7th or the y to the 7th. I just did that for purposes of showing what the 7, choose 0 and the 7, choose 7 were and how it relates to the Pascal's triangle. So this is by far my favorite way to go. However, if you are interested in a faster way to calculate the coefficients, what you can do is utilize your TI if you're able to. Feel free to read the notes below and you will see that if you plug in your n choose r to your calculator, so let me see if I can do that with you really quick. You will end up getting the row of Pascal's triangle that you're interested in. So again, I go to my y equals. I have some previous stuff I will get rid of. And we're going to use this in terms of a variable. In all cases, if you go back to the binomial theorem, just really quick again, you'll notice that the top number in every single one of these n choose r situations, it's always 7. So it remains constant the whole time. It is the bottom number that changes. So, and actually it changes with a nice pattern, 0, 1, 2, 3, 4, 5, and so on. So if you go back to your TI, love this part. That is at least if we do get to use a TI. If you don't, then just use the Pascal's triangle or go through your formulas. We're going to call up the combination notation, but I'm going to enter 7 in for the first part. So I'm going to press the math key, go to probability, and item number 3. And I'm going to do 7, choose X, because that is what is changing. It's varying the whole way through. So now, my friends, this is not really looking for a graph. All we have to use is the table feature in our TI. So we could say second graph for the table feature. And if you want to go with pressing from 0 to 7, 0, 1, 2, 3, 4, 5, 6, and 7, and ignore anyone else afterwards because that's not part of the Pascal's triangle, you will see, and I think I might have put this in some of the notes, it kind of depends. Depends where you're coming from or looking for this, but you'll kind of see the relationship. I would like to prove it to you, which I find really, really, really cool. See if I can paste it right here so you all can see. I'll make it a little larger because it is hard to see in a video, at least for me. If you guys would humor me a bit, check it out. Look at the 7th row, or maybe it's not the 7th row of Pascal's triangle, but x plus y to the 7th, we end up getting the same values. So that's a very nice way to take this. Let's say you want to build the 30th row of Pascal's triangle. Well, who would ask you that? That'd be super mean. But you can do it relatively fast if you do have the use of the TI as well. So I hope this helps. We'll be doing a couple more of these either in the homework or together. Just get the hang of the pattern, and there's really less to memorize. I'll see you in the next example.